Hello guys, this is your boy Anant and let's get straight into the video. Today our topic is backtracking with matrices I believe. What do I say? I don't know man. But whatever, let's get into it. If you already don't know how neural nets are represented as matrices, you search on Google, you will get it. It's simple. Every input layer is a matrix and every weight layer is another matrix. And suppose let's say an input is a 1 cross 3 matrix and our output layer is a 1 cross 4 matrix. We need a 3 cross 4 matrix as a weight matrix, because see, when you multiply 1 cross 3 dot product 1 cross 3 and 3 cross 4, you'll get 1 cross 4 matrix. That's how the entire neural network system works. With that out of the way, let's get started. Let's say this is our neural network. Input layer is x0 and the next weight layer is w1 and the next input layer is x1 and our final so on, and our final output is x3 with the 3 nodes, right? This is let's say our target output, like the output of expected output is y, and our activation function is f of x, right? Activation function is something like sigmoid function or tanh function or anything you want, right? Let's say it's a f of x. So then you should remember this clearly. X1 equals to f of x naught w1, right? W, yeah, this one, see? And x2 equals to f of same thing, right? You know this, right? Okay, if you don't know this, you should go back and see other tutorials. This is purely the actual back propagation, how these weight matrices are updated. This video is about that. Now you should ignore b1, b2 and b0 because these are biases and these things we don't update during this back propagation method, so it's unnecessary. Or even if when we differentiate, so it will be anyways gone while differentiating because it's a constant, so better avoid it before, right? So that it's simple for us. Now let's assume the error function to be e, which is half of y minus x whole square, where y is our target and x3 is our output. And that's it. Now we need to calculate how much this output is being affected by this w3 matrix, right? So, and then we need to update it. So first, what is the differentiating factor? How much is w3 contributing to the error? We need to reduce that. So in order to reduce that, we differentiate this uh, in order to find out that error, we differentiate it with respect to w3. And if you don't know, d by differentiation of x square is 2x here, and differentiation of f of g of x is f dash g of x into g dash x. So we need to use both those properties in this derivation a lot. With that, Now, clearly you can differentiate this and x3 minus y into partial derivative of f of w3 x2, which turns out to be x3 minus y into f dash w3 x2 into, this is what I told you, f of g of x, f dash of x into derivative of g f dash of x into g dash of x, which is here g of x equals to w3 x2, so g dash of x equals to do by do of w3 x2. So clearly x3 minus y into f dash w3 x2 into x2, let's say this x3 minus y into f dash w3 x2, uh, let's assume it to be k3, and so this error, what we have to calculate, I mean the difference in error, I'd say the contribution to error, I'd say, is k3 into x2, where k3 is this constant. Now let's do the same thing for w2. You will see why I did this in a second, but yeah, now we need to calculate it for w2, the second weight matrix in the neural network. It's the same thing. Now the problem is here, in this case, in the above case, x2 was a constant. It does not matter to in the case of w3, because x2 is not affecting the output x3 directly, right? It's with, I mean, w3 is the what do you say, variable, but in this case now partial derivative w2 is the variable, so we need to find what other variables are dependent on w2. So x3 is clearly dependent on w2, right? So how is x3 dependent on w3 w2, you ask? x3 is equal to w3 x2, you got it? So awesome. Then it will be simply x3 minus y into f dash of w3 x2 into dou w3 x2 by dou w2, as I told you before. Now clearly this x3 minus y into f dash of w3 x2 into w3 into dou x2 by dou w2, get it, right? Now what is x2? X2 is clearly w2 x1, right? So expanding that, and this this x3 minus y into f dash w3 x2 can be here, it can be replaced as k3 and w3, and this is dou x2 by dou w2, k3 into w3 into dou f dou w2 x1 by dou w2, right? k3 into w3 into f dash w2 x1 into dou w2 by dou dou x dou w2 x1 by dou w2, which means it's simply dou e by dou w2 equals to k3 w3 into f dash w2 x1 into x1, because this thing x1 here is a constant, it doesn't matter, it does not depend on w2 anyway in any manner, right? Let's assume k3 w3 into f dash w2 x1 as k2, right? then dou e by dou wt equals to k2 x1. If you understand this, you understood all the above things, right? So be careful here. Now we need to calculate for the first weight layer. I mean, you can do this infinite times until, if there are many layers, you can do this many times. You'll see how this will explain everything, how it recursively is the same thing over and over again. So let's say we need to calculate the W1, the first matrix, right? Now, error with respect to error contributed by W1, that's what we are finding. Listen carefully. Uh, it's the same thing as I told you before, half of x3 minus y whole square. And if you partially derive it with respect to W1, you will get x3 minus y into dou of x3 by dou of W1. And x3 is f of w3 x2, and x3 minus y into f dash w3 x2 into dou of x w3 x2 by dou of w1. You know, f of g of x derivative is f dash x, f dash g of x into g dash x, the same thing. And dou of e by dou of w1 equals to k3 w3 into dou x2 by dou w1. See clearly, this x3 minus 1 into f dash w3 x2 is what? K3. And this w3 will come out, and dou x2 by dou w1 will remain. Now you can see the pattern why it's repeating k3 w3. Similarly, you get k2 w2 out. I'll show you how, don't worry. And f dash w, this is clearly same thing. F of g of x is f dash x into g dash x, f dash g of x into g dash x. So f dash w2 x1 into dou of w2 x1 by dou w1, k2 into w2 into dou of x1 by dou of w1, because k2 is equal to k3 w3 into f dash w2 x1. And this w2 will come out, and with respect to x1, it's dependent on how x1 is dependent on w1 is like this way, x1 equals to w1 x naught. And now we can take x naught out because it's a constant, and f dash of w1 x naught into x naught will come out, and d dou w1 by dou w1 is 1. So clearly, let's say k1 equals to k2 w2 into f dash of w1 x naught. So let's say that, and so then the contribution will become k1 x naught. So you can clearly see the pattern. uh, k1 is dependent on k2, and k2 is dependent on k3. So if we just find k3, we can find k2 and k1 and k0, and how many other layers there. From the final output layer, you can go to n number of infinite backward layers as long as you uh, computers allow. In theory, there might be multiple layers. So yeah, there you go. The error with respect to w3 is k3x2, error with respect to w2 is k2x1, and error with respect to w1 is k1x0. So if there is an nth layer, I'll show you. If there is an nth layer, the error will be this. For the nth layer, I mean for the last layer, the error will be this kn will be this xn minus y into f dash wn xn minus 1, right? For any other layer, for all the previous layers, we calculate ki. If we get this ki, we get this error, right? So we need to calculate that ki, right? For that, we can clearly see it is none other than ki plus 1. Suppose we need to calculate, let's say, k2. What should we do? K3 into W3 according to this formula. W3 into K3 into F dash of W3 into X2, right? See, this is not the same thing. K3 into W3 into F dash of W2 into X1. The same thing, right? For if it works for K1 also. K2 into W2 into F dash of W1 X0, right? For K3, it's this thing, the output minus target into F mod into F dash of W and Xn minus 1, W and W3 into X2 in our case. So how do you find the error? It's simple. We got the Ki. Now what we need to do for any ith layer, just need to multiply it by the previous layers uh, values ki into xi minus 1. Alright, now once you get that, you can use in stochastic gradient descent functions, or whatever functions you want to minimize the error, where alpha is the learning rate. Yeah, there you go. Now, many people have a doubt, how do I calculate the derivative of a matrix while calculating k? This f dash w I x I minus 1, how do I get this, right? Let's say we have, this is a practical example. Let's say our x0 is 101 and w1 is 111010, and now we need to, what would be the output of this? This output would be 1 cross 2 matrix, and this one w1 x0 is 2 comma 0. Let's say f of x equals to a sigmoid function, or any other function for that matter. Let's say if it's tan h, you calculate, I'm calculating for sigmoid function because it's the most common function for tutorials, I guess. I don't know. Now if we find the derivative of this function, if you find the derivative of this function normally, that is e power 1 by 1 plus e power minus x, it will be f of x into 1 minus f of x, right? So now x1 is, what is x1? Like function of w1 x0, right? Function of w1 is x0 is none other than 1, it is 1 comma 0 comma 1, right? Oh my god. Yeah, function of w1 x0 is nothing but 1 by e power, this function, you substitute these values 2 and 0, right? x1 is 1 by 1 plus e power minus 2 and 1 by 1 plus e power 0. Now you know where I'm going, right? If it's f dash of x, you'll find this multiplication, and this is f dash x, right? This is f dash x. Basically, this is f dash x, right? Now you substitute the same 2, this 2 comma 0 here, e power minus 2 plus 1 by e power minus 2 whole square. This is your f dash x, right? That's it for this video. Now you got how to calculate f dash x and f of x, and you know how to calculate the error, and you know how to calculate the k. These are the very important equations. You just need to calculate kn and f dash n, and then you'll get ki for any layer, anything you want until k is 0. And that's the end of the video. GG, goodbye. One more important thing, if you want to check this out, what do you say, matrix representation of neural networks, right? If you go, I saw this somewhere, of course. I guess I should see, this is our equation, right? Z of x equals to w1 x1 plus w2 x2 plus w3 x3. I'll show how it's transformed into neurons. See, a normal neural network, any neural network for that matter, will have this. We need to w1, w2, w3 is our weight matrix. These blue lines represent the, as you can see, the connection to the blue node, green lines to the green node, and orange lines to the orange node. And x1, x2 are our previous input nodes, and when we multiply them, we get what we want: w1 x1, w2 x2. You want this, right? Multiplication w, let's say this is w1, w1 x1 should go to a1, w uh, w2 x, this whatever, w2 x2, we got this one, and like that. So it's the same thing, same idea, but it's, when you do it in matrices, it's very simple. As I said, this is what 3 cross 4 matrix, and this is what 4 cross 1 matrix, and 3 cross 4 into 4 cross 1 will, what will it uh, what will it result in? 3 cross 1 matrix. There you go, 3 cross 1 matrix with 3 output nodes. That's how this all the neural networks in the world work for right now. And that's it. GG. I hope there are no other clarifications. And said that, this is Anand signing off. You can follow me on LinkedIn or Twitter if you want. No, sorry, not Twitter. You can come to Rocket League, and we can play some games. If you want any further videos about any specific topics, you can leave the comments. And also, if you want a code, implemented code of this video, you can comment, and I can explain the code as well. Uh, saying that, signing off. GG.